We are going to discuss network basics. Why you want to study network theory? It is a must for electrical engineering, electronics engineering, and instrumentation engineering. It is a compulsory requirement for analysis of analog electronics, digital electronics, control system, communication engineering, power system, power electronics, machines. Gate weightage 7 to 10 marks. Relatively easy to grasp and chances of scoring full marks in GATE and ESC exam. So we'll start from basic elements. So this is a basic element, positive current and voltage convention. The basic relations is dq upon dt. That is, current is the time rate of change of charge. Example, if q passing through the element is defined by 3t square for t greater or equal to 0, what is the current for t greater or equal to 0? So simply use the relation I is equal to dq upon dt, which will give you 6t for t greater or equal to 0. Another example, if current plot is like this, I in milliampere, 1, 0 and 2, this is your 1.5 milliampere and this 2 milliampere. What is the total charge passed through the element? So you know the relations. Q is equal to minus infinite to final time I dt. So here, so 0 to 2 I dt. So it will give you the, see, if you do the integration it is okay, but you can see that this is the area needed, that is 1.5 into 1 plus 2 into 1, that is 3.5 millicoulomb. Clear? Next example. Why I am discussing more and more example is it will complement your preparation for the GATE and other competitive exam. What is the number of electrons passed through an element in 1 second for 1 ampere of current? You will use the basic relations I is equal to Q upon T. So you require the Q is equal to, I is the 1 ampere, T is the 1 second, so 1 coulomb. You know that each electron has the electronics charge of 1.6 into 10 to the power minus 19 coulomb. To make 1 coulomb, we required one upon E, number of electrons. 1 upon E is your 6.24 into 10 to the power 8. These many numbers of electrons when passed through in any element in 1 second will produce 1 ampere of current. 1 mark question. We will discuss potential is an important parameters for electrical engineering. V potential V is equal to charge rate of change of energy, and energy is equal to minus infinite to final charge V dq, and your power is equal to rate of change of energy dw upon dq into dq upon dt, which is voltage and current. This part is a voltage and this part is current. So using this relation, w is equal to minus infinity to t v I d tau. Example, voltage across an element is 3 e to the power minus 2t for t greater or equal to 0, and the corresponding current flowing through that element I is equal to 1 upon 6 e to the power minus 2t for t greater or equal to 0. I mean to say, this is any element, current flowing through this, and this is your voltage V. So question is, what is the energy dissipated at t equal to 250? So you need to find energy at t equal to 250 millisecond. Let us calculate. We know that power is equal to V into I. So 3 e to the power minus 2t and 1 upon 6 e to the power minus 2t. So when you multiply both together, you will have 1 upon 2 e to the power minus 4t. So energy E, and this voltage and current starts from 0. So 0 to final time is the 0.25 second, because 250 millisecond, and half e to the power minus 4t dt. So a simple integration, minus 1 upon 8 e to the power minus 4t 0 to 0.25. So you will get minus 1 upon 8 e to the power minus 1 minus e to the power 0, that is 1. So you will get the 1 upon 8 into 0.63, and if you divide with your calculator, you will get 78.75 millijoule. These type of questions are very basic questions, and they keep asking in the GATE in different format. So always starts from your basics, which is very much essentials if you are really serious about your GATE exam. Let us move to the convention. Current voltage conventions I have already discussed some part. Let us have a rule, and you should follow this rule. Any element, whether it is a voltage source, resistors, capacitors, inductors, or in general, I'll draw a rectangular box. So positive current will be flowing through this direction. If this direction current, actual current match, so it's a positive current. Similarly, the current entering the terminal is the positive voltage. Right? Print in your mind these things. So we'll discuss the basic element. So first one will be your resistor. So voltage and current relations for the resistors are V equal to I into R and I equal to V upon R. Power is equal to VI, instantaneous power. Then energy, you know relations, minus infinity to T P tau d tau. Then inductor, these are very basic relations. You are expected to know in very minutely. You should not have any doubt in all these basic relations. Inductor is simply a coil and the value is L. So voltage is the L di upon dt, and the current is 1 upon L integration minus infinity to T V tau d tau. So this is the voltage and current relations. It's a very basic relations. So P equal to VI, energy stored in the inductor, is integration P then d tau. We have a relations for energy calculation or energy stored in the inductor. I'll just derive that one. Energy by definition is the 0 to final time. At what time you and how much energy is stored. So I have to integrate from 0 to TF. I am assuming that current and voltage starts at t equal to 0. So P, that is VI dt. So 0 to TF. V is your L di upon dt and I dt cancel. So you have 0 to final time L I di. When you do the integration, you have L by 2 I square 0 to final time. So if at time t equal to TF, your current is the I is equal to capital I, and at t equal to 0, I equal to 0, then you have energy equal to half L I square. So energy stored in the inductor is the half L and current flowing through that at that time. So half L I square. Then we'll move to the capacitor. Draw the capacitor. See, this is a current, this is the voltage. Basic relations are I is equal to C dV upon dt, and voltage is equal to 1 upon C integration minus infinity to T I d tau, right? And instantaneous power P is equal to VI. Energy is equal to minus infinity to T P tau d tau. You know, this is this type of integration when we integrate from T, so you just change the variable here. Obviously power is a function of time, it will be, and when you integrate you have to change the variable. Then we'll calculate the energy. Energy is equal to 0, I am considering from 0 to final time, then VI dt, which is 0 to final time. V is your written the V, I C dV upon dt, and dt cancel. So you have C. I am assuming C is constant. Obviously in the circuit your C will be constant, otherwise if C is a function of time you have to include the C inside. So 0 to TF V dV, which will give you the C by 2 V square, then 0 to TF. If at time TF t equal to TF, your V is the capital V, that is it has charged up to this value of voltage, particular voltage, and it starts from 0, that is t equal to 0, your V equal to 0, then energy stored in the capacitors will be the C by 2 V, right? So when using all these relations, always prefer the basic relations. Sometimes question set may twist you with the energy calculations. So whenever using the formula, so be cautious for that. Suppose they ask you what is the energy stored in the capacitor at certain time, and you find the voltage at that time and put into these relations. But sometimes they will ask how much energy has been drawn from the battery. That time, suppose this is a battery, this is a voltage and current. How much energy drawn from this? Same way you use the relations. Find the voltage is here and the current, then integration for that time dt. That much energy will be drawn from that battery. Always remember, resistors dissipate energy and capacitors and inductors store the energy. We'll do some example to have a clarity on whatever we have studied till now. Consider the current waveform T in millisecond, I in ampere. Check this circuit. It's a capacitors which is 100 microfarad, and this is your current. You need to find voltage V, how much, at t equal to 3 millisecond. So V equal to 1 upon C integration of minus infinity to t I d tau. So here 1 upon C starting from 0 to 3, because at 3 millisecond, and I dt, which is 1 upon 10 to the power minus 4 into this is area under current curve, and that area is the area of triangle, that is half into 2 into 1 millisecond plus area of rectangle, that is 2 into 1 millisecond. So you have this area 10 to the power minus 3, because to represent the millisecond. So you will have 3 into 10, that is 30 volt. If they ask you the energy stored in the capacitors are 3 millisecond, assuming the ideal capacitor, energy equal to half CV square, half, and your C is your 100 microfarad, so 10 to the power minus 4 into V square, 30 volt, that is 900, that is 0.045 joule or 45 millijoule. So always use the basic relations if it looks the question is complicated or they have twisted the questions.